Okay, Assalamualaikum. Good afternoon, everyone. Let's start our class for this afternoon.
Good afternoon, Doctor.
Okay, so we continue from this morning, yeah. Okay, so this morning I have explained to you about the sensible heat. Yeah, so sensible heat is basically the heat associated when you have the change in temperature. Okay, so the next type of heat is the latent heat. Okay, so of course the heat of the latent heat you can also have when there is a change from solid to liquid or from liquid to solid. Yeah, but we for this chapter we are only concerned with the latent heat of vaporization. So it involves the change of phase or state from liquid to vapor or from vapor to liquid. Yeah, so um, the latent heat of vaporization. So in this case, we are dealing with pure substance, okay? Meaning you only have a single substance. The initial condition is saturated liquid at T1 and P1, okay? And the final condition is saturated vapor at T1 and P1, yeah? Because when you have the change from liquid, okay, vaporize, meaning that it changed to gas or vapor. And again, for latent heats, remember the temperature will be at the same temperature. Okay, there is no change in the temperature, and also we assume constant pressure, same pressure also. Okay, so in this case, there is no change in the temperature, but there is a phase change. Yeah, and there is no work involved. So for the latent heat of vaporization, the heat here is equal the change of enthalpy of vaporization. Okay, so to determine the latent heat of vaporization, there are basically these four equations that we can use to determine the heat, the latent heat of vaporization. Okay, all right, so the heat, heat of vaporization is the heat that is required when a pure substance is liquefied from solid or vaporized from liquid at constant pressure. No change in temperature occurs. Okay, basically this is the definition of latent heat. Okay, and then this is the first equation for the heat of. Sorry, this is equation 4.11. Let me check. Okay. All right. So the first equation is the Clapeyron equation. Okay. So the change of enthalpy, which is the latent heat, is equal the T, okay, temperature, times the delta V. Yeah? So delta V is the volume change accompanying the phase change, and then times dP set over dt. So for this Clapeyron equation, it can also be applied for besides the heat of vaporization, you can also apply when there is a change from solid to liquid. Yeah, so it's a general equation. But as I mentioned before this, we are more interested in the change from liquid to vapor because it is a more common phenomenon that we face in chemical reactions or chemical engineering. Okay. So in this case, the P sat is the vapor pressure. Okay. So for vaporization of a pure liquid, dP sat over dt is the slope of the vapor pressure versus temperature curve at the temperature of interest. Okay. So we can find dp set over dt if you plot the graph of vapor pressure versus temperature. Because at different temperature, you will have different vapor pressure, right? Okay, so you can we can plot the graph, and then you can take the slope. So the slope, and then take that the slope at the temperature of interest. Okay, and delta V is the difference between molar volumes of saturated liquid and saturated vapor. Of course, when you have liquid and vapor, the molar volume will be different, right? So vapor normally will have larger volumes compared to liquid, and delta H is the latent heat of vaporization. Okay, delta H can be calculated from vapor pressure and volumetric data. Okay, so the second equation is the Troughton's rule. So it gives the rough estimates of latent heats of vaporization for pure liquids at their normal boiling points. Okay, so for Troughton's rule, it's a very special case in which it gives the heat of vaporization at the normal boiling point. Okay, normal boiling point ni it depends on the substance. Okay, so kalau water, the normal boiling point is 100 degrees Celsius lah. Okay, you can get this Tn value at the back of the appendix B. Dekat situ ada Tn values for each of the species substance. Okay, so you can estimate using this Troughton's rule. Okay, where you just need the value of R, okay, which of course you know, and then the Tn, which you can get from the appendix. So this ratio between the heat of vaporization at the normal boiling points divide with the divide with R times Tn is approximately 10. Okay, and these are some of the values of this ratio for specific compound. So roughly it equals 10. But if you look at the specific compound, for example, argon, for argon, this is actually equal 8. Okay. For nitrogen, it's 8.7, oxygen 9.1, and so on. But roughly it is, for all the types of species, roughly it's about 10. Okay, another equation is the one proposed by Rydell. So for the Rydell's equation, we still have the delta Hn, which is the heat of vaporization at the normal boiling point, but it gives a more elaborated value here lah. Okay, so just now you ada sama lah depan ni kan, delta Hn over Rtn. Okay, but for Rydell you have this value, this formula here. Okay, so 1.092 bracket ln PC minus 1.013. Okay, close bracket, and then the below part is this one. And here we have the parameter Trn. So Trn is basically the reduced temperature. The reduced temperature at the normal temperature, normal boiling point. Okay, so Tn over Tc. Okay, and then PC is the critical pressure. Okay, estimates of the latent heats of vaporization of pure liquid at any temperature from the known value at a single temperature may be based on a known experimental value on the value estimated by equation above. The method proposed by Watson has found wide acceptance. So for the Watson's equation, you can determine the heat of vaporization at condition 2 when you have the heat of vaporization at condition 1, okay, or at temperature 1, okay. So in that case, let's say state 2 is represented by number 2, okay, so you can determine delta H2 when you have the information of delta H1. Okay, so this is example 4.4. All right, so example 4.4. Given that the latent heat of vaporization of water at 100 degrees Celsius is 2,257 joule per gram, estimate the latent heat at 300 degrees C. So in this case, you have the information of state 1, okay, latent heat of state 1. You want to know the latent heat of state 2. So we can use Watson's equation, yeah, yang this one, the last equation. Okay, so here we have delta H1, which is the latent heat at 100 degrees C, equals 2257 joule per gram. And then delta H2 is the latent heat at 300 degrees C, which we want to determine. And then TR1, okay, this is the reduced temperature at the first temperature. So 100, convert to Kelvin, divide with TC. So TC, you have to get the value from the appendix. Okay. So for water, TC is 647.1. Okay. So we get TR1. And then TR2 is the reduced temperature at 300 degrees C. Okay. So we get this value. So just substitute into the Watson's equation. Okay. So we get the answer here. So delta H2 is 1371 joule per gram. Okay, so this is the result of when we use the formula by Watson's. But if we compare with the value given in the steam tables, okay, if you refer to the steam table, so remember I have shown you the steam table before this, right? You can check from appendix F, okay? The value given by the steam tables is 1406. Okay, so yes, there are some differences here, but it's okay. You know, it's roughly the same. If you round this up to to the closest hundreds, kan, you dapat lah 1,400. Okay, so it's almost the same. Okay, so basically that's it lah about latent heat. Latent heat. There are 4 types of equations. Okay. The Clapeyron equation, this one, and then the Troughton's rule, the Rydell's equation or the Rydell's rule, and then the Watson's equation. Okay. All right. So next we move on to the heat of reactions. Okay. So for the previous sections, okay, the heat effects are for physical processes. Okay. When you have the physical processes in terms of the phase change or in terms of the temperature change. Okay. So chemical processes also accompanied by transfer of heat and temperature changes. Most of the heat effects for chemical reactions are calculated in a standard way. Later I will explain to you what is the standard, okay, in heat of reactions. Okay. And the heat of specific reaction depends on both temperature of reactants and the products. Okay, first we need the information on the process. So when you have chemical reactions, you can write the reaction in terms of the chemical punya reaction kan, okay? So you can have this information. Okay, first is the feed. Yeah, feed, for example, A1, A2, so they are the reactants. And then the outlets, they are the products of the reaction. And then the heat is either released or absorbed during the process. Okay. For the exothermic, which is heat release, the delta H becomes negative. When endothermic means the absorb the heat, then delta H becomes positive. Okay, so standard heat of reaction. So what is the standard for heat of reaction? So it is defined as the enthalpy change from a stoichiometric reaction where the reactants entering at standard state. So what is the standard state? Okay, so T is at the specific temperature and then P is at 1 bar. Okay, and then for specified phase, so it can be in gas, liquid or solid, and the products are also at specified phases and the same standard state. Okay. So in this case, the product dia mesti sama temperature T and then at the same pressure lah. Okay. Alright. So in this case, the heat effect for this heat of reaction will be the change in enthalpy, and then which is the summation of the enthalpy of species I, okay, times the stoichiometric coefficient. So this symbol yang macam V ni, but this is actually a Greek letter which is called nu, okay. This nu I is the stoichiometric coefficient. Okay, and then this symbol degree ni is referring to the standard state. Okay, so when you have this degree symbol, it refers to standard state. So dekat sini pun adalah, this is for the individual enthalpy for each species. Okay, alright. So a standard state is a particular state of a species at temperature T and at specified conditions of pressure, composition, and physical condition, for example, in gas, liquid, or solid. So a standard state pressure of 1 standard atmosphere, which is equals 101325 Pascal, was in use for many years as the standard pressure, but now they have changed the standard to 1 bar. Okay, so 1 bar is equals 10 to the power of 5 Pascal. Okay. Okay. For the composition, the standard states are pure species. Okay. So for gases, the pure substance in the ideal gas state at 1 bar. So untuk gas, kita consider dia as ideal gas for the standard condition, standard state. Yeah. For liquids and solids, they are real pure liquid and solid at 1 bar. Alright, so of course, you have many reactions, and you know these chemical reactions, they can occur at different temperature, right? But normally we refer to the temperature, this temperature, 298 Kelvin or 25 degrees Celsius. So there are many references for tabulated data for delta H not 298, or this is the standard heat of reaction at 298 Kelvin for commonly found reactions. Okay. However, to tabulate all possible reactions are not practical because we have so many types of reactions, right? And furthermore, not all reactions can take place at 298 Kelvin. Okay. So we can calculate the standard heat of reaction from standard heat of formation of the reactants and products. Okay, so in this case, we can calculate the standard heat of reaction for that specific reaction from the standard heat of formation. So dekat sini kita tambah subscript F to show that this is the standard heat for formation, yeah, formation reaction. Okay. Now, what is a formation reaction? So formation reaction is a reaction which forms a single compound from its constituent elements. Okay, so the syarat dia ataupun the rule is you must have the elements as the reactant, and then you have a single compound as the product. Okay. And then the heat of formation is based on 1 mole of compounds formed. So dekat sini dia 1 mole. Okay. So when we write the equation, you have to first base on 1 mole of compound, of product, and then from there you can balance lah your reaction. Okay. And it must be elements dekat sini Alright, yang ini saya dah explain tadi. So this is the symbol we use for the standard heat of formation. Okay, delta H, and then we have this degree symbol, and then F for formation, and then this is the temperature 298. Okay, So an abridged list of values is given in table C4 of appendix C. Okay, so this is specific for the temperature given here lah. Okay, 298. Right, yang ini dah sama je dengan, this is the same as the previous slide. Alright. Okay, what are elements? Okay, so elements is basically the simplest molecule that can exist in nature. Okay, so for example, for carbon, C, of course, carbon C is the simplest possible molecule lah. Okay, but for oxygen ataupun hydrogen ataupun nitrogen, you cannot have O sahaja. It must be in O2, betul tak? And hydrogen also must be H2. Nitrogen N2. You cannot have just H or N. So element is the simplest molecule that can exist in nature. Okay. All right. Let's take a look at table C4. Okay. So I will show you how you can read the values from the appendix. This is appendix C. Okay. Yeah, okay, this one. Okay, so this is table C4. Okay, pagi tadi saya dah tunjuk juga actually. Okay, the first three tables are for the heat capacities. And then the C4 is for the standard enthalpies and Gibbs energies of formation at 298.15 Kelvin. Okay, and take note that the unit here is joule per mole. Yeah, joule per mole of the substance form. Okay, so you have the chemical species here, okay, and then the chemical formula, and then this is the state, okay. All right, and then you have the standard heat of formation, and then the standard Gibbs energy. So yang Gibbs energy ni later we will use in chapter. I cannot remember which chapter, but we will later use this value also. Okay. All right. Now, okay. So please take note that for some of the substances, they are given in different phases. Yeah. For example, ethanol. Tengok dekat sini ethanol dia ada dalam gas and ada juga dalam liquid. So the values the heat of formation is different when they have different, when the substance has different phase. Okay. Same goes methanol, toluene, water also. So sometimes pelajar selalu salah ambil value for water. Yeah, okay. So you have to take note whether the substance is in gas or in liquid or in aqueous or in solid. So because you have different values for different state, different phase. Okay. Okay, so we go back to this PowerPoint. Okay, I will skip this for now. Okay. All right. So example 4.5. Calculate the standard heat at 25 degrees Celsius for the following reaction. Okay. So you are given this reaction for HCl in gas plus O2 in gas yield or it produces 2H2O in gas plus 2Cl2 in gas. Okay. So in this in this chemical reaction, we can find the standard heats of formation at 298.15 Kelvin from table C4. Yeah. So here you can find the values for HCl in gas, which is a negative 92307 joule. Okay, and then for H2O in gas, negative 241,818 joule. Okay, so in this case, okay, I will show you basically two methods, but they're actually almost the same lah. Okay, so the first method is you can break down the equation into several equations, yeah, and basically you break it down into the reaction for the formation reaction. Okay, so first we have on the here the first substance or the first compound is HCl, yeah, 4HCl. So in this case, for HCl in gas, we can apa tu? This is like a reverse reaction of the formation reaction. Sebab formation tu is from elements, kita dapat produk, kita dapat compound kan. Tapi sekarang daripada compound tu kita jadikan dia element. So this is like a reverse formation reaction. Okay. So in this case, we can break it out into H2 element and then Cl2 element. And then you just do the stoichiometric balance lah. So kita ada 4 dekat sini. So you have 2 here and 2. So in this case, the heat of the standard heat of reaction here is 4 because we have 4 HCl, 4 moles, and then times 92307. And please note that sebab kat sini negative because this is for the heat of formation. Dekat sini tak ada negative because this is the reverse of the formation reaction. So dia jadi negative dekat sini, dia jadi positive. Okay, yeah. For the second one, okay, sorry. So this is HCl and then next you have O2. Okay, O2, it is already an element. So daripada elemen nak jadi elemen, so tak ada lah. So that means you can skip O2, which means that the heat of reaction, heat of formation for O2 is 0 lah because it's already an element. Okay. Okay, next we have H2O. So you can write the formation reaction for H2O. So from H2 O2, you get H2O and you balance the equation. Okay, so we get this because we have 2 moles of water. Okay, and then you times the heat of formation for H2O. Okay, so yang ini kita maintain lah simbol dia negative because it is from element to product. Okay, so the addition ataupun the summation, kalau you tambahkan reaction yang pertama dengan reaction yang kedua, kita akan dapat the final reaction which is same with this one, right? So in this case, kita boleh tambahkan saja the heat of reaction. So this heat of reaction yang pertama tambah heat of reaction yang kedua akan dapatlah the heat of reaction for the final equation, the final reaction yang ini. Okay, so the answer is negative 114,408 joule. Okay, so this is if you want to break down the equation into the chemical reaction into several formation reaction, but you can actually just use the tadi kita ada formula yang ini kan, this one. You can just write in terms of this formula. So tadi the standard heat of reaction at 298 is equals, sorry, sometimes it just it's a bit difficult to write. And this is delta H not F 298. Okay, ada 8 kat sini. Okay, so in this case, okay, untuk stoichiometric coefficient ni, actually this comes later sebenarnya stoichiometric coefficient ni. So for the stoichiometric coefficient, for the product, it will be positive. For the reactants, it will be negative. So in this case, you have the reactants HCl. So this is the nombor yang kat depan is the stoichiometric coefficient lah. So for HCl is -4, and then O2 is -1, H2O is +2, and Cl2 is +2. Okay, so you just sub into the equation. You have here is -4 times the standard heat of formation yang ini, -92307 plus O2 tak adalah because dia elemen kan. So we have H2O, so this is 2 times -241,818. So samalah, you akan dapat jawapan yang sama juga dengan ni. Cuma cara kita buat tu lain sikit lah. Okay. So this is equal this one. Alright. Okay, next is about standard heat of combustion. Okay, so only a few formation reactions can actually be carried out, and therefore data for these reactions must usually be determined indirectly. Okay, so in actual case, yeah, in real life, not all formation reaction can occur, from elements and then you get that product. Yeah, so if we are going to get the data for these reactions yang tak boleh occur naturally, then we need the data for some other reaction. So one of those reactions is the combustion reaction. Okay, so combustion reaction is defined as a reaction between an element of compound and oxygen to form specified combustion products. Okay. For example, this reaction, formation of N-butane. Okay, this reaction, okay, from carbon and hydrogen to get N-butane cannot be carried out in practice. Okay. However, this equation results from combination of the following combustion reactions. Okay, so kita tak boleh nak dapat directly formation like this. So we have to combine several other reactions to get the formation reaction. So this is like macam hypothetical punya formation lah. It doesn't exist naturally. Okay. So in this case, we have this first reaction. So between carbon and oxygen. Okay. To get CO2. And then you have H2 plus O2 to get H2O. And then CO2 plus H2O to get C4H10 and butane and oxygen. Okay, so in this case, this formation reaction is actually a combination of these three equations. Okay, and we can calculate the heat of reaction for each individual reaction here. And the total will be the heat of formation for this N-butane. Okay. Right. Next is the temperature dependence of delta H. Okay. So to calculate the standard heats of reaction at other temperatures from knowledge of the value at the reference temperature. So remember just now we only have the values for 298, yeah, ataupun 25 degrees Celsius. So what happens if we have other temperatures, right? So now is how we will learn how to calculate the delta H, the standard heat of reaction for other temperatures. Okay. So first, you may write the general chemical reaction like this. Okay. So we have this stoichiometric coefficient. Okay, and then you have the compound. Okay, stoichiometric coefficient and then the compound. Okay, so the ones that come before the arrow is the reactants, and then after that you have the products. Okay, so here VI or nu I is a stoichiometric coefficient, and AI stands for chemical formula. Okay, so the The stoichiometric coefficient is positive for products and negative for reactants. Okay, so the new I with their accompanying signs are called the stoichiometric numbers. Okay. So this sign convention allows the definition of a standard heat of reaction to be expressed mathematically by the equation this. Okay. So the standard heat of reaction, okay, is defined as the total of stoichiometric coefficient times the enthalpy. Okay. So here H zero ataupun H naught I is the enthalpy of species I in its standard state, and the summation is over all products and reactants. Okay. So yang new I ni tadi, kalau dia product it's positive, kalau dia reactants it will become negative. Okay. Okay, so the standard state enthalpy of chemical compound is equal to its heat of formation plus the standard state enthalpies of its constituent elements. A standard state enthalpies of all elements are arbitrarily set equal 0 as the basis of calculation. Okay, here you have this where the summation is over all products and reactants. I think kejap question ni macam okay, kejap heat of formation plus the standard state enthalpies of its constituent elements with the standard state enthalpies of all elements. Oh, okay. Okay. Okay, this equation is okay. This is 4.14. This is equation 4.14. Sorry. Yang tadi salah. This is ada salah sikit. Okay, this is 4.14. This is 4.14. Okay. Okay, so yang ini H0I, this one. So H0I is the enthalpy of species I in its standard state, and the summation is over all. Okay, sorry. Yang ini lah. So H0I is the enthalpy of species I. So the enthalpy of species I is equal to its heat of formation plus the standard state enthalpies. Maksud dia yang ini H is equals, dia kata kat sini equal to its heat of formation. So the heat of formation plus the standard state enthalpies of its constituent elements. So plus enthalpy of dia punya elemen lah. Katalah ada elemen 1 and then element 2 and so on. Okay. Okay, and at standard state, the enthalpies of all elements are arbitrarily set equal 0. So yang ini semua kita boleh set dia 0. Okay, 0. So that's why kita tinggal yang ini sahaja. We are only left with this one. And that's why we can sub into the previous equation. So sepatutnya dekat sini ada delta. Here, dia ada delta. Okay, so the standard heat of reaction is equal the stoichiometric number times the standard heat of formation for that substance. Okay, and you take the summation. And this is equation 4.15. Okay, example. This is an example. We have a reaction here. 4HCl in gas plus O2 in gas produces 2H2O in gas and 2Cl2 in gas. So in this case, we can write the standard heat of formation, standard heat of reaction as this, yeah. So equal 2 times the standard heat of formation for H2O. This is 2 positive lah sebab dia product. Okay, and then minus 4 because here is the number is 4 and then it's a reactant, so dia jadi negatif lah. Okay, times the standard heat of formation of HCl. Okay, so ini adalah cara yang saya tunjuk tadi kan dekat example ni. Mana tadi? Yang ini. So it's the same way. Okay. Right. So you can get this heat of formation from the appendix and then you can just substitute into this equation here. Okay. Alright, so next we have the temperature dependence of delta H 0 ataupun standard heat of reaction. Because in the heat of formation, you are only given the values for 298, yeah. So if we consider other temperatures, then we need to, to use this equation. Okay, 4.18. Okay, so actually this equation dia datangnya daripada equation it's actually coming from this equation. Sorry, dH equals okay. This is the equation from the definition of specific heat at constant pressure (CP). So daripada sini kita integrate dia, and then you based on the definition of standard heat of reaction. Standard heat of reaction. Kita akan dapatlah finally this equation 4.18. Okay, so you can refer to the textbooks macam mana dia derive from dH equals CP dt until we get this equation 4.18. Okay, so basically for the standard heat of reaction, okay, for other temperatures, yeah. So dekat sini is equal standard heat of reaction at the reference temperature. So reference temperature ni kita tunjuk kat sini lah, 0, another 0 here. And then plus R integration of T0 until T times delta CP dt. Okay, so this symbol yang bulat di atas ni is also menunjukkan the standard value. Okay, where delta H degree atau zero ni and delta H 00 are heats of reaction at temperature T and at reference temperature T0 respectively. Okay. So yang ini kalau ada simbol kat bawah ni, this is the reference temperature. Yang ini ialah dekat actual temperature. Okay. Right. So from the first part of this chapter, sensible heat, kan, kita dah belajar macam mana nak calculate CP, okay, which is depends on the R. Depends on the T, temperature, okay. So dekat sini, perbezaan dia, if you notice, there's a symbol delta dekat sini, kan, delta. In the previous section, sensible heat punya section tu, kita tak ada guna simbol delta ni. Sebab apa? Sebab that one is just for pure compound, pure substance, one substance only. Okay. But now when you have a reaction, it will be several compounds. Kan, contohnya tadi macam ni kan, you have 4 compounds involved. Okay, HCl, O2, H2O and Cl2. So delta ni menunjukkan sort of macam average value. Okay, so here you have the delta. Okay, so delta Cp over R dt integration is equal, sama je macam yang sebelum ni, cuma you have that delta lah sebelum A, B, C and D. Okay, and here the definition of delta A, delta B, delta C and delta D is the summation of the stoichiometric numbers for each of the compound times the the value for A, B, C, D lah. Okay. So and then we also have this equation kan, using the bracket yang segitiga tu. Okay. So in this case also the same. We have the delta here, delta A, delta B, delta C and delta D to show that this delta ni comes from this lah. You take the summation for all the compounds, yeah. So sama juga macam dalam sensible heat yang tadi tu, we can express this as IDCPH. Kalau dia tak ada delta, we just kat sini tak ada D lah, so ICPH tadi kalau dia single compound kan. But now you have the D to show that this is a mixture. Okay, so it becomes ada D ni, maksudnya ada delta kat sini lah. Okay, so IDCPH for this integration punya form, and for this one it becomes MDCPH. Okay, so now so now the equation then becomes this. Okay, so you can either write in this integral punya form like this, or we can use this alternative form, this one, in terms of delta Cp bracket segitiga ni. Okay, and again remember when you use this form you have to times the temperature difference. Okay, alright, this is example 4.6, page 141. Okay. Calculate the standard heat of the methanol synthesis reaction at 800 degrees C. Okay, and the reaction is given here. CO in gas plus 2H2 in gas menghasilkan methanol CH3OH in gas. Okay, and you need to find the temperature given here is 800 degrees C. Okay, so now okay, so we have to use equation, either you use 4.21 yang ini ataupun 4.18 yang ini. Okay, so in this case first you need to find the standard heat of reaction at the reference temperature, which is 298. Okay, so this one we can get from the standard heat of formation. Okay, so you find the standard heat of formation for methanol and the standard heat of formation for CO lah. Okay, H2 tak ada because dia element. Okay, so in this case, we write the product first. So the stoichiometric number for methanol is 1 plus 1, positive 1. Okay, so tak ada apa-apa kat sini. And then minus is because here is the reactant. Okay, so for CO, the stoichiometric number is negative 1. So it becomes minus kat sini lah. Okay, and times the value of standard heat of formation for CO. So we get the value here for the standard heat of reaction at 298. Okay. Now, sekarang kita dah dapat yang the first term ni tadi. Okay, we have determined this one. This one sama Now, we want to calculate the second term, yang bahagian kedua dekat sini ataupun dekat sini. Okay. So in this case, you need to find the values of A, B, C, D for each of the compound. So we can make a list like this. Okay, so you list out the products and then the reactants, and then you write down the stoichiometric number. Okay, for CH for methanol is +1. Okay, for CO is -1. For H2 is -2. Okay, next you list out all the parameters A, B, C, D. Okay, so yang ini ambil dekat table C1 tadi lah. Okay, so just list out everything, and then we can calculate the delta A, delta B, delta C, and delta D. Okay, yang ini from the definition tadi, this number times the stoichiometric number. So ini plus ini darab ini, yang ini darab ini, yang ini darab ini, and you take the summation, take the total, dapat delta A. So same goes with delta B. Ini darab ini, yang ini darab ini, yang ini darab ini, you take the total, dapat delta B, and then similarly dapat yang ini delta C. Okay lah, because only one compound kan yang ada C, so it's just the same as this. For D also you take the summation. Okay. Right, so once you have determined the delta A, B, delta A, delta B, delta C, and delta D, we can use the equation. So in this case, dia guna equation 4.19. This equation 4.19. So dalam buku teks dia bagi solution based on this equation lah, yang the integral punya form. Okay, so you just substitute delta A, delta B, delta C, delta D, and then you calculate the tau. Tau is your final temperature divide with the standard temperature. Yeah. So standard tadi ialah 298. And then your actual temperature is 800 degrees C. You convert to Kelvin first. Okay. So after substitution akan dapatlah this value, the IDCPH value yang ini. And then so for this format, kalau format ni ditulis macam ni, so IDCPH, this is T0, this is T0, this is T, and then this is tau, and then sorry, this is not tau, this is delta A. This is delta A, and then you have delta B, delta C, delta D. Okay. Alright. And then by equation 4.18, equation 4.18 tadi, this one kan. Sorry, pause. Delta H plus dengan R Cp delta Cp. Okay. So this integral value is the IDCPH lah. Okay. So that's why we have to, sorry, kat sini ada R. Supposed to have R here. Okay. Right, so you just substitute yang ini tadi kita dapat dekat here, okay. And then you need the R and then times the this value, okay. Now, if you use the alternative equation, which is 4.20 in terms of this, the MDCPH, first you calculate the MDCPH, we get this value, okay, and then you just sub into the equation. Remember, you have to take the temperature difference as well dekat sini, okay. So we get this answer. Yeah, so it's almost the same lah. Negative 103,568 joule. Okay. Alright, so for the standard heat of reaction yang ini this value negative 103,568 joule ni, this is specific for the reaction given. Ni, yang ini. Okay, so if let's say you so in this case it is for 1 mole of methanol because ini satu kan, tak ada apa-apa means satu lah. But if let's say you add 2 here for 2 moles, katalah letak 2 kat sini kan, so ini jadi 2, ini jadi 4. So in this case the standard heat also will be times 2 lah. So yang tadi dekat sini pun this value you kena darab 2. Okay, so the value calculated is based on the stoichiometric numbers ataupun stoichiometric coefficient tadi. Okay. Alright. Okay, next we go to example 4.7. Okay, example 4.7, what is the maximum temperature that can be reached by the combustion of methane with 20% excess air? Both the methane and the air enter the burner at 25 degrees C. Okay. Okay, so in this case, first you can write the balance equation, reaction. So you have the combustion of methane with 20% excess air. Okay, so first when we have combustion reaction, so it must be the compound plus oxygen. Okay, so you can write methane CH4 plus O2. And then in this case, we assume that it's a complete combustion. So complete combustion, it will yield CO2, carbon dioxide and water. Okay, so first in this case, we just write CH4 plus O2 dapat CO2 plus H2O and then you balance lah the equation. Okay. And another one is that we also assume here that the water is in gas. Okay, because we assume that the exit ataupun the output punya temperature tu is high, so that the water becomes vapor. Okay. Alright, so first you can calculate the standard heat of reaction for this reaction at 25 degrees C. Okay, so in this case, okay, so you can find the standard heat of formation. First, kita dapatkan standard heat of formation for each of the compound from appendix C4. Okay, so you dapatkan untuk CH4, untuk O2 tak ada because it's an element, and then for CO2 and then for H2O. Okay. So here we have this. This is the value of heat of formation for CO2. Yeah. And then because the stoichiometric number is 1, yeah, positive 1 because it's a product. So dekat sini dia akan jadi macam ni lah. And then for H2O, you get 2 because kat sini ada 2. Okay, and then this becomes negative because it's a reactant. Okay, and then you get the values for heat of formation of CH4. Okay, so the total is negative 802,625 joule. Okay, since the maximum attainable temperature, called the theoretical flame temperature, is sought, assume that the combustion reaction goes to completion adiabatically. Maksudnya dekat sini Q is 0, meaning that there is no heat supply from supplied from outside. Okay, so the change in temperature, the raise in temperature is only caused by the heat of reaction. Okay, so in this case Q equals 0. If the kinetic and potential energy changes are negligible and shaft work equals 0, the overall energy balance for the process reduces to delta H equals 0. So for purposes of calculation of the final temperature, any convenient path between the initial and final states may be used. The path chosen is indicated in the diagram. Okay, so kita boleh tunjuk dia punya path ya, theoretical path tu like this diagram. Okay, so first you have the reactants dekat sini. So reactants enter at standard condition, standard pressure which is 1 bar and then 25 degrees C. Sebab dia dah bagi dekat sini 25. The question already stated here, both methane and the air enter the burner at 25 degrees C. Okay, now this question is a bit tricky ya, sebab dia kata methane tu masuk dengan air. Okay, but the combustion reaction only involves oxygen, kan? So in this case, kita kena tengok dalam air tu dia bukan ada oxygen sahaja, dia ada nitrogen juga. Okay, so in the inlet dalam reactants mixture tu, you will have methane, and then you will have O2, and then you have N2, nitrogen, because it's coming from the air, because you don't supply pure oxygen, yeah? Okay, and then from the reactants, it becomes the products. So products ni first kita biar dia dekat temperature yang sama. So same pressure, same temperature, so 1 bar. Here you have the products at 1 bar and 25 degrees C. And then from here, baru kita increase the temperature to the final temperature, assume as T. Okay. So here you have the products at 1 bar and T, final temperature. Okay. So here dekat sini, daripada reactants to the products at the same temperature, this is the heat involved lah. So the standard heat of reaction at 25 degrees C. And then from the products daripada temperature 25 to T, this is another heat which is represented by delta HP. P ni menunjukkan dia produk lah. Okay. Okay, so the total heat effects ataupun total enthalpy will become the summation. Okay, so yang ini plus ini. So it is written here, delta H equals delta H 0298 plus delta H 0P. Okay, and this is 0 sebab tadi kita assume dekat sini dia adiabatic. So there is no external energy or additional heat supplied to the system. Okay, so heat yang dekat sini yang menyebabkan temperature ni naik is only caused by the heat of reaction here. Okay, so when 1 mole of methane burn is the basis for all calculations, the following quantities of oxygen and nitrogen are supplied by the entering air. So first kita kena tahu berapa mol yang terlibat ya. So let's say kita gunakan basis 1 mole of methane burn. Okay. And you have this reaction. Tadi. Let me just write the equation again. Kita ada CH4. Gas plus O2. Gas. Get CO2. Gas and H2O. Gas. Okay. And then if you balance the equation, dia ada 2 kat sini and then 2 kat sini. Okay. Alright. So using the basis of 1 mole of methane, if you have 1 mole of methane, you need 2 moles of oxygen. Okay, based on this stoichiometric balance, yeah. So 1 mole kat sini, you need 2 moles. So moles oxygen required is 2. Okay, sekarang ni dalam soalan dia nyatakan 20% excess air. 20% excess air. So, because 20% excess, so dekat sini, you have to times 0.2 lah. Okay, because there's 20% excess. So, percent excess, tadi 20% times the moles required. So, for oxygen, 2 moles. So, because of that, you get the 0.4, which is the amount of excess oxygen. Okay. And then, for the moles of nitrogen entering, kita calculate dia like this. Okay. So most oxygen required is 2 and then you have excess is 0.4. So the total moles of oxygen is 2.4. Tak tulis kat sini. So this is okay, total O2 is 2.4 moles. Okay. So daripada oxygen ni, we assume that the air is composed of 21% oxygen and 79% nitrogen. So air kita assume dia 21% oxygen and 79% nitrogen. Yeah. Okay. So from this ratio, you can calculate the moles of nitrogen here. Yeah. So yang ini total mole of oxygen times this ratio dia lah 79 over 21. So kita dapat moles of nitrogen entering. So you can write the number of moles here. Okay, we have 1 mole CH4, 2.4 moles of oxygen, and then 9.03 mole of nitrogen. Okay. And then similarly, you also need to find the moles of the products. Yeah. So products tadi, so for the products, okay, you have to refer again to the reaction yang dekat sini. Okay, so for product, you will have 1 mole of CO2 and then 2 moles of H2O. And then sebab tadi kita ada excess kan, excess oxygen. So the excess oxygen will also, you can find it at the product stream. So 0.4 ni ialah excess oxygen yang tidak bertindak balas dengan methane. And then of course you have the nitrogen because nitrogen does not take part in the reaction. Okay, so these are the mole numbers for the product stream. Okay, so okay, inilah tadi. Okay. Alright, so now untuk dapatkan value of delta HP ni tadi, because it's a sensible heat actually, because it's the heat that is caused by the change in temperature. Yeah, so your starting temperature is the is 25 degrees C ataupun 298.15 Kelvin, and then the final temperature is assumed to be T. Okay, so we can use the equation for the sensible heat lah. Okay, so in this case you have to calculate the CP, okay, mean heat capacity yang ini. So in order for you to calculate the CP, you need the ABCD. Okay, so same as the example before, the difference is here is that yang example sebelum tadi kita list out all the products and the reactants kan, and then you have to know the stoichiometric coefficient. Tapi yang ini kita hanya listkan untuk product stream sahaja. Okay, because dekat sini composition dia sama. Yang ini semua jumlah mol ni dekat bawah ni pun actually the same thing. So the composition, the product stream tu it does not change. What change is only the temperature. Okay. Berbanding yang tadi, bila you take into account the whole reaction, dia ada perubahan. I mean, you have the different reactants and the products. Okay. So it's slightly different. Okay. And instead of the stoichiometric coefficient, kita listkan dia punya mole number. Okay. So that's why you need to calculate the mole kat sini lah, yang ini ni. Okay, you have to know the mole. Okay, so you list out the list of you list out the compounds in the product stream, and then you write down the mole number, and then you find the A, B, C, D from the appendix, and then you find the delta. Okay, delta A, delta B. In this case C tak ada. Okay, so just delta D. Okay, and then baru boleh dapatkan CPH over R. So we use this equation. Okay, yang ini saya tak tulis delta lah, but actually you are using the delta lah. Ini sebab dia ada delta sebab dia mixture ya. Okay, so in this case kita tak dapat calculate tau. Yeah, dalam equation we have tau, but you cannot determine tau because you don't know the final temperature. So in this case, kena buat iteration lah. Okay, right. So here, what is the equation? Saya tak tunjuk dekat sini. Okay. Okay, so you have to use this equation. Tadi kan kita dah determine the this one. You have determined the delta H 0298. Okay. And then dekat sini kita ada yang ini the energy balance becomes this, delta H sama dengan yang ini plus ini equals 0. So in this case delta HP is negative delta H298. Okay, yang ini. So dia jadi positif Okay, so tadi kita ada equation this one is negative delta HP 0. Okay, so yang ini is negative delta HP. Okay, so delta HP dia jadi positif. Yeah, so you have to be careful here. Sebab kalau you salah ambil positif jadi negatif, negatif jadi positif, nanti you punya calculation T tu dia akan berubah lah. Okay, so okay, so in this case, this is the equation. H. Okay, right. So, okay, so to solve using iteration, okay, saya masukkan value dia dulu. So delta HP is 802,625. And then untuk CP ni you tak boleh dapat terus, you kena you can calculate CPH over R. Okay, so this is CPH over R times R, which is 8.314, and then plus 298. Okay, your standard temperature. Okay, so here in this case, let's assume that the T is 500 degrees C. Yang ini sebenarnya it's macam mana you nak determine ni, saya tak ada tips lah. Normally I just put any value yang higher lah than 25 degrees C, than the initial temperature. Okay, if you are lucky, kalau you punya tekaan tu is very close to the actual answer, your iteration will become very short. Okay, but if your estimate for the first estimate here, kalau you teka tu jauh jawapan dia daripada the actual answer, then normally the iteration will take longer lah. Okay, so in this case I assume that the first we start with 500 degrees C. Okay, convert to Kelvin, so you can calculate the tau, you can calculate CPH over R, and you can calculate T using this equation yang ini. Okay, so now using the new T, okay, new T, recalculate tau, recalculate CPH over R, recalculate T. Okay, and then we repeat sampai dah dapat converge. So in this case, I get the answer as 2066 Kelvin. Dalam buku teks, buku teks pun dapat jawapan sama ya. T equals 2066 Kelvin or 1793 degrees Celsius. So this is your answer lah. So this is the maximum attainable temperature for that reaction. Okay. So up to this point, do you have any questions? Ada tak soalan? Okay, so okay, I see. Okay. Okay, so we will move on to the last part of chapter 4. Chapter 4 ni, in terms of the content, dia sebenarnya tak banyak. Tapi, how to say, bila kita bagi soalan tu, the question will sometimes give you combination of different types of heat. So in terms of the calculation, the jalan kerja tu dia sebenarnya panjang, banyak lah. You need time to solve the equation, the problem. Walaupun dari segi theoretically tak banyak pun. Okay, you just need to understand the sensible heat, and then kalau dia ada phase change, you need to calculate the latent heat, and if it involves chemical reaction, you will have to calculate the heat of reaction. Okay. Okay. Oh, okay. So this is just actually the solution lah. Solution from the textbook. Okay. Yang tadi ni saya terangkan is cara saya step by step. Sebab kadang-kadang dalam textbook ni dia tak tunjuk step by step solution. They just show which equation and then the final answer. So this one is the solution based on the textbook. Okay. Okay. All right. So example 4.8. Okay. Okay, so example 4.8. One method for the manufacture of synthesis gas primarily a mixture of CO and H2, is the catalytic reforming of CH4, methane, with steam at high temperature and atmospheric pressure, which is indicated by this equation. Sorry yang ini sepatutnya tak ada plus minus ni. Okay, it's just a plus lah. Okay, so CH4 gas plus H2O gas dapat CO gas plus 3H2 gas. Okay, the only other reaction which occurs to an appreciable extent is the water-gas shift reaction. Okay, so this is like a side reaction. Okay, CO gas plus H2O gas dapat CO2 gas plus H2 gas. Okay, so if the reactants are supplied in the ratio of 2 mole steam to 1 mole CH4, and if heat is supplied to the reactor so that the products reach a temperature of 1300 Kelvin, the CH4 is completely converted and the product stream contains 17.4 mole percent CO. Assuming the reactants to be preheated to 600 K, calculate the heat requirement for the reactor. Okay, so can you see how complicated it is, you know, in actual industrial setting, yeah? You have like inlet ataupun reactor tu dia masuk kat different temperature. Okay, and then inside the reactor adalah reaction yang terlibat. And then at the same time, you also have some side reactions, okay, byproducts. Okay, and then dekat outlet tu, temperature dia berubah lagi. Okay, so this is, you know, just to show you how complex it is, you know, in the actual industrial setting, and it requires your knowledge, you know, the combination of different types of heat effects. Okay, so let me show you the solution. Okay. Sekejap saya tengok solution. Okay, so the solution from the textbook is given here, but I will also explain how I would do the calculations, because in my case, I prefer to use the MDCPH punya equation rather than the IDCPH. Okay, dalam buku teks ni dia bagi solution. Okay, yang ini dia pakai MCPH. Okay, never mind. Just sometimes they use the IDCPH or ICPH. So anyway, okay, let me just explain cara saya solution ya. Okay, so first we can write the reaction. Okay, you have the main reaction, which is this one, yeah. So methane plus H2O dapat CO plus 3H2. And then you have the side reaction, which is this reaction. So side reaction ni tadi ialah from the first reaction you get CO kan. So CO daripada first reaction ni dia react pula dengan water dalam side reaction. So the side reaction will give CO2 and H2. Okay, and then you can write down all the information given from the question. So first we have the inlet. So dalam inlet tu kita ada CH4 1 mole and then H2O 2 mole. Ni if the reactants are supplied in the ratio of 2 mole steam to 1 mole CH4. So kita dapat daripada sini lah. Okay, so you get 1 mole here and 2 mole of steam ataupun water in gas. Okay, right. So from this inlet mole information, we can actually calculate based on the stoichiometric balance. Okay, so dekat sini kita ada 1 mole, ada 2 mole, and then from the reaction, from the balance stoichiometric reaction ni, daripada sini kita ada 1 mole lah, because kat sini 1 kan, and then you have 3 moles H2. Okay, and then from this CO, sebahagian daripada CO yang ini, dia akan terlibat dalam side reaction. So we don't know this value. So just assume X. Okay, so X mole and then react with X mole, dapat X mole here and then X mole here. Okay. So, we can calculate the outlet dekat sini. Okay, so for the you have to list down all the outlet punya composition lah. So you have the CO, and then ada H2, ada CO2, and also the so ada CO, ada H2, ada CO2. Ini H2 sama. Oh yeah, and you have the excess H2O. Sebab H2O ni dia excess kan. Sepatutnya you just need 1 mole. But dalam reactant stream tu ada 2 mole. So you have extra excess. So the excess will also go to the outlet stream. Okay. So here, okay. So first we have this for CO. So CO ni you kena calculate lah. Ni this is the material material balance lah. Okay. So 1 mole terhasil and then tolak X mole reacted in the side reaction. So 1 minus X. Okay. And then for H2O, H2O is you have ada 2 mole tapi 1 mole dah digunakan. So you have 1 mole extra, and out of that 1 mole extra, X mole is actually involved in the side reaction. Okay, so 1 minus X for H2O. For CO2 is easy lah. You just get from the side reaction, so X. And then for H2, you get from both the main and the side reaction. So 3 plus X. Okay, so when we take this total, dia dapat tepat-tepat 5 mole. Okay, and then from the question, it is given here, the product stream contains 17.4 mole percent of CO. Okay, so we have this information, percent of CO in the outlet is it's 17.4%. So if you convert to perpuluhan, dia jadi inilah 0.174. So 1 minus X, the mole of CO over total mole in the outlet ataupun product stream is equal 0.174. Okay, so from here we can calculate X. So dapatlah X 0.13. So dapat 0.13. So now you know the actual mole number of the product stream. Okay. Right. So so in this case, kita boleh lukis hypothetical path like this, yeah. You can draw your hypothetical path something like this. So you start with the reactants. So the reactants is at 600K. Tadi kan dalam soalan dia sebut apa? Okay, assuming the reactants to be preheated to 600K before entering the reactor. Okay, so it starts with 600K, and then sebab kita nak kira standard heat of reaction tu, dia cuma ada dalam 25 degree C saja. Okay, those values from the appendix kan, you only have the values for 25 degree C ataupun 298 Kelvin. So kita kena reduce dia kepada 298 Kelvin. This is just hypothetically, okay, just for the sake of calculation. Of course dalam actual condition, actual punya reaction, you tak adalah nak dah lepas heat dia 600 nak turunkan kepada 298 pula kan? Tak. This is just for calculation, and that's why we call it hypothetical. Okay. So hypothetically kita reduce kepada standard temperature, which is 298. Okay, so you have the reactant stream ataupun inlet stream at 298, and then this reactants dia akan jadi product. So here you have the standard heat of reaction. So this is the product kat sini, starting from here. So product dekat 298. Okay, daripada 298 you have to increase to 1300 Kelvin. Sebab tadi dia kata dekat sini here. Okay, so the products reach a temperature of 1300 Kelvin. Okay, so the products final temperature dia ialah 1300. Okay, so kita boleh lukis macam ni. So here is the sensible heat because of the reactant stream. And then this is the standard heat of reaction. This is the sensible heat caused by the product stream. And then yang menghubungkan antara starting and the final point is the total heat total heat lah ataupun the enthalpy change. Okay, so right, so the balance dia akan jadi delta H sama dengan delta HR plus delta H298 plus delta HP macam tu. Okay, but okay, now what's complicated here is that you have two reactions, kan? You have the main reaction and then you have the side reaction. So you have to consider the you have to consider the heat of reaction from both reactions. Okay, so that's why here I wrote reaction 1, the main reaction, and then reaction 2. So first you find the standard heat of reaction for reaction 1 and reaction 2 based on the values of the standard heat of formation. So samalah macam tadi, you find the stoichiometric kat sini. So the standard heat of reaction is based on the stoichiometric balance, stoichiometric numbers, bukan the actual mole number. Okay, so be careful on that. Okay, so we calculated here kat sini, and then the total will be the inilah yang ini total heat of reaction. Okay, now untuk calculate the reactant stream, okay, the sensible heat. So again, you need to find the values of A, B, C, D. Okay, so you list out the compound dekat dalam reactant stream. So you have CH4 and H2O. Okay, and then the mole number, and then the A, B, C, D, and then you get the delta. Okay, so you can use the formula CPH over R, dapatkan value. Okay, in this case you need the tau. Okay, and get the delta HR. Okay, which is the R times CPH over R times the temperature difference. Okay, so temperature difference ni, here you have to be careful because the temperature difference will be final temperature minus initial temperature. Okay, so final temperature dia ialah 298. Okay, and initial temperature is is 600. So you kena careful lah. This must be final minus initial. Otherwise nanti you akan dapat simbol yang lain. Ya, kat sini dia akan jadi positif kalau you terbalik. Okay. So tadi kita dah calculate the heat of reaction and then the heat of the reactant stream. So this is the heat of the product stream. Okay, sama juga proses dia. You have to list out all the compounds in the product stream, and then the mole number, the actual mole, and then A, B, C, D, and then find the delta. Okay, you can calculate tau, you can sub into CPH over R, dapatkan CPH over R, and then you get the delta HP. Okay, so dah dapat semua tu, you boleh total up untuk dapatkan delta H. Okay, so you get the answer 328011 joule. Okay, so this is the answer. Alright. Yang ini, this is the saya sebut tadi, ni solution based on the textbook. Sama jugalah, dia akan dapat jawapan yang sama. Where's the answer? Oh, yeah, okay. So this is the answer, yeah. So the heat requirement here is inilah total enthalpy, which is 328010. Tadi saya dapat 011. Okay, so almost the same lah. Okay. And this result is on the basis of 1 mole CH4 fed to the reactor. Okay. Alright. Okay, we have another example, 4.9. This is the last example, kan? Okay, yeah, this is the last example. Okay, example 4.9. A boiler is fired with a high-grade fuel oil consisting only of hydrocarbons, having a standard heat of combustion of negative 43,515 joule per gram at 25 degrees C with CO2 gas and H2O liquid as products. The temperature of the fuel and air entering the combustion chamber is 25 degrees C. The air is assumed dry. The flue gases leave at 300 degrees C, and the average analysis on a dry basis is 11.2% CO2, 0.4% CO, 6.2% O2, and 82.2% N2. Calculate the fraction of the heat of combustion of the oil that is transferred as heat to the boiler. Okay. All right. Okay, so you are given this information. You have the standard heat of combustion of the hydrocarbon. Okay. So disebut dekat sini fuel oil which consists of only hydrocarbons. Okay. So this is the standard heat of combustion. And then you have the temperature of the inlet. And then you have the temperature of the outlet and then the composition of the outlet. And then you need to calculate the fraction of the heat of combustion that is transferred as heat to the boiler. Okay. Sebab tadi kita apa tu? Kita gunakan okay, sorry, never mind. Okay, so based on the information, first we need to list out the the inlet and the outlet. So same lah macam the previous example. First you need to list out the inlet stream and the outlet stream. Okay, reactant stream and the product stream. So in this case, we can take a basis of 100 mole dry flue gases. Okay, so this is the composition of the outlet product is given here. Yang ini composition outlet. So 11.2 mole sebab dia bagi persen kan. So kita assume dia 100 mole lah for easy calculation. So kalau ada 100 mole because it's 11.2%, so you have 11.2 mole. Okay, and then here is 0.4 mole, 6.2, 82.2, so total will be 100 mole. Okay, this is just for easy calculation. Of course, you can assume 1 mole. Tapi kalau 1 mole, nanti you akan ada point, banyak 0 point dia kan. So, for convenience, we choose 100 mole. Okay, so next. In the question, you are only given given this information hydrocarbon. So hydrocarbons saja. So you don't know the exact formula for the hydrocarbons, but we know that hydrocarbons is basically composed of C and H. Yeah, hydrocarbon dia cuma ada carbon dan hydrogen. Okay, so in this case kita tak tahu the exact formula. So we can write as CXHY. Okay, sebab kita tak tahu formula dia. But this is a hydrocarbon lah. Okay, and then it's a combustion reaction. So combustion reaction dia mesti plus O2 gas kat sini. And then dapat CO2 and H2O. Okay. Okay, dia sebut sini with CO2 gas and H2O liquid as product. So dekat sini it specifically mention liquid. So you have to write down liquid here. Okay, and then you have to do the balance lah, stoichiometric balance, kena calculate based on X, Y, okay. Dapatkan balance dia, so dapat macam ni lah. Okay. And the standard heat of reaction for this reaction is given from the question. negative 43515 joule per gram. So this is per gram of this hydrocarbon. Okay, betul kan? Per gram. Yes. Okay, so now we can calculate the mole of okay, so we need to calculate the mole, tapi kita tak tahu, there is no information on the inlet kan. We only know the composition of the outlet. So kita kena derive the inlet composition from the outlet composition. So sebenarnya saya buat yang bawah ni dululah. Okay, we list out all the composition for the outlet, and then daripada sini kita tahu that we have nitrogen 82.2%. Sorry, this is 82.2 mole lah, because kita assume 100 mole total mole. Okay, so from this 82.2 mole kita derive back to this air composition in the inlet. And because nitrogen does not take part in the reaction, so nitrogen outlet dengan inlet samalah mole dia, still 82.2. Okay, and then we can calculate for oxygen. So kita assume tadi 21% oxygen and 79% nitrogen. So kita darabkan lah, this is based on the ratio lah. Okay, so daripada sini dapat oxygen is 21.85 mole. Okay. Yeah. And then, okay, another tricky part here is sebenarnya dekat outlet ni before compounds kan, dia sebenarnya ada H2O juga. Kenapa ada H2O? Because reaction hydrocarbon punya combustion ni dia menghasilkan, okay, so that's why we have water, H2O juga dekat outlet stream. Okay, now okay, and for this water dekat outlet ni, because of the high temperature, so it has to be in gas. Okay, so walaupun dekat reaction yang the main reaction it gives in liquid, tapi dekat outlet tu dia jadi gas lah. Okay, and then another thing is that here 0.4%, yang ini diberi daripada soalan ada CO, tapi dalam reaction ni kita tak ada CO, betul tak? So there is a side reaction here, okay, that gives CO in the final composition. Okay, so CO ni sebenarnya datang daripada incomplete combustion. So in this case kita boleh dapatkan dia daripada CO2 lah. It's actually from the CO2. So from the CO2 it becomes a CO and also O2. Okay. And then we also have the reaction of water, yeah. So daripada liquid kepada gas for the outlet stream. Okay. So based on all the information, you kena you have to find all the unknowns. Yeah. And saya letak Z lah, because kita tak tahu berapa banyak actually CO2 yang so I put Z here. Okay, material balance here, I write down the material balance. Okay, you write ini kan, CO2 dia terhasil X mole, okay, tapi Z mole terlibat dalam side reaction, so the balance will be X minus Z, which is equal 11.2. Kita dapat given 11.2 mole. Okay, and then for CO is Z lah, sebab kita kat sini Z, dia terhasil Z, and then also this is given 0.4. Kita tahu dia 0.4 drives yang extra sini is 11.6. Okay, so you dah dapat X, dah dapat Z, dah dapat Z, so you can calculate Y. Sebab kita nak dapat, kita ada Y lagi dekat O2 ni, X plus Y over 4. So kita dapat Y 17, so you boleh trace balik lah berapa mole exactly semua. Okay, right. Okay, so based on that X, Y, Z punya value, kita boleh dapat the actual reaction punya, so tadi kita dah tulis dekat sini, we here, this is the reaction for 1 mole of hydrocarbon. So dah dapat berapa, Y berapa, so boleh substitute balik lah dalam ni. So this is after substitution. Okay, this X tadi 11.6 and then this is Y 17. And then you get the actual mole of O2 and then for CO2 and then H2O. Okay, and you also get the balance for the material balance for reaction 2 and also reaction 3. Okay, alright. Now, here, okay, so for the standard heat of reaction, you are given the value in terms of joule per gram. Okay, tapi sekarang ni kita nak dapatkan per mole. Why? Sebab nanti kita punya calculation of outlet stream and inlet stream will be based on mole, betul tak? So we have to convert into mole first. Okay, so you have to know, you have to calculate the molecular weight of the hydrocarbon lah. So you can calculate because kita dah tahu formula dia kat sini kan. So you can calculate the molecular weight of the hydrocarbon and then based on the heat of reaction per gram ni darabkan dengan molecular weight, so kita dapatlah values in joule per mole. Okay, so this is for reaction 1, which is the combustion, the main reaction. At the same time, you also have to calculate the standard heat of reaction for reaction 2 and reaction 3. Okay, reaction 2 ni tadi ialah from CO2 kepada CONO2, and for the reaction 3 is the change of phase, water from liquid phase to gas phase. So dapatlah dekat sini. And don't forget to consider the mole number, sebab kita punya calculation ni is based on the actual mole that you get from the reaction. So in this case, the second reaction you have to times 0.4, okay, sebab dia ada 0.4 ni, basis dia is 0.4 mole of CO2, okay. And then for the second equation you have, the third reaction you have to times 8.5, okay, sebab ada 8.5 dekat sini. Okay. Alright, so untuk yang standard heat reaction you dah dapat, so it's the total of the 3 reactions. Okay, so you get the total here. So okay, so you can write the hypothetical path like this. Okay, so inlet tu dia masuk dekat 25, so samalah dengan standard heat, standard temperature, so no problem. So you can go straight to the standard heat of reaction, and then the outlet is at 25. And then only you increase to 300. Okay, so dekat sini you ada sensible heat of the product stream. Okay, untuk inlet stream tak ada sebab dia dah memang masuk dekat standard temperature, which is 25. Okay, right, so to calculate the product stream heat for the product stream, you have to list out the components, the composition of the product, and then dia punya mole, and then A, B, C, D, and then you calculate the delta A, B, delta A, delta B, delta C, delta D. In this case, lucky lah sebab tak ada C. Okay, so it makes your calculation much simpler if you don't have C. Okay, and then you can calculate your tau, and then masukkan dalam equation CPH over R, and then you dapatkan delta HP. Okay, so R times CPH over R times temperature difference. So here is the final temperature minus Final minus initial temperature. So dapat sini 940,625 joule. Okay. Right. So total heat to the boiler is inilah delta H. So total heat to the boiler is heat from the reaction plus heat that is caused by the increase in product stream punya temperature. So this is the total. And then the question, dia nak, apa soalan ni tadi? Soalannya panjang Fraction of the heat of combustion of the oil that is transferred as heat to the boiler. So in this case, fraction of heat of combustion of the oil. Fraction of the heat of combustion of the oil that is transferred as heat to the boiler. Okay. So in this case, saya terbalik ni. Okay, so heat transferred to the boiler is this, and then this is the heat of combustion, right? Heat of combustion here, okay. Oh, okay, betul lah, right. So the fraction, berapa banyak fraction? So daripada total heat of combustion ni, a fraction of that is actually transferred as heat to the boiler. So heat to the boiler tadi kita dah calculate is this value. So this value divide with the heat of combustion lah, yang ini, this one. Okay, so we get the fraction in terms of percentage, which is 79%. So dekat sini, okay, so here you can actually ignore the symbol positive or negative, because positive negative dalam heat ni dia represent whether the heat is released or whether heat is absorbed, yeah. So kalau kita just nak when we are referring to the amount, to the magnitude only, then you can ignore the plus or the negative sign, yeah. It's just, we are just considering the amount here, okay. So this is the fraction, 79%. Okay, that's all. Actually, we have finished chapter 4. Ada soalan tak? Since we have finished chapter 4 this week, next week is also allocated for chapter 4 actually. So kita ada extra time. So I plan to do tutorial for chapter 3 and chapter 4 next week. Yeah. Okay. Ada soalan tak? Any question? Alright. Kalau tak ada soalan, we can stop here. Right. Okay, boleh So I will stop here. We have finished chapter 4. Basically, chapter 4 is